Let's look at the sea surface temperatures again to go into precipitation and sea level pressure. You probably already heard of hydrostatic pressure, where basically the Earth is so large that the ocean and atmosphere are like thin shells on top of the Earth's surface, and the depths are much smaller compared to the horizontal scales. So we make some derivations later on to show that the vertical motions in most cases are much smaller than the horizontal motions. So you assume that the balance in the vertical is basically between the weight of the fluid above and the pressure. So using that, you can kind of relate the warm sea surface temperatures to low sea level pressures, but also warm sea surface temperatures tend to have large evaporations, and the air gets heated and begins to rise and take that moist air with it, which expands and condenses in the atmosphere to produce clouds and rains and so on. So these warm regions in general are very heavy rain regions as well. This region should get about 5 meters per year of rainfall, and of course this band of warm temperatures also corresponds to convergence of the trade winds, which we will look at from the southeast and the northeast. And when you have convergence, that means air is going up, so there is a continuity that requires that the rising air be replaced with horizontal convergences. So those are rainy regions as well, and warm sea surface temperatures. And you can see that both the South Atlantic and the South Pacific have these convergence zones as well, called the South Pacific Convergence Zone and the South Atlantic Convergence Zone, which is not as prominent as the South Pacific one. And Indian Ocean is complicated, as we will see in the rain as well. So here is the rain. Looking at millimeters per day again for the boreal summer, autumn, winter and spring months, and you can clearly see the rain bands here now, which is the 8 millimeter per day contour capturing the high amounts of rain, which should amount to something like 3 meters per year, I think. You can calculate 365 times 8 per, so approximately 3 meters. And since we are starting with boreal summer, you can immediately see the interesting feature here over the Indian Ocean. The ITCZ here is clearly to the north, with a small piece of SPCZ here, and SACZ, or the South Atlantic Convergence Zone, is not as obvious. But the Indian Ocean, which remains warm throughout the year pretty much, holds on to the marine ITCZ here, and the ITCZ is kind of split to produce rainfall over India and Bay of Bengal and these regions. But of course this is the summer monsoon season for India, and there is a little maximum rainfall here that you cannot see clearly because there are western Ghats here that will squeeze rain out of these southwesterly winds coming into the landmass and having to climb the western Ghats and dumping rain because of orography, right? And that those winds also produce very strong cooling here, which is not so obvious, but you can still see it, the cooling, which kind of reduces the amount of rainfall. So you will get rainfall over East Africa during both the inter-monsoon seasons, so so-called long rains in March, April, May, and the short rains in September, October, November. And West Africa has, of course, a so-called African monsoon as well. Maritime continent has rain pretty much throughout the year, but its drier season is during June, July, August. It gets more rain during DJF, and its large interannual variability, year-to-year variability in rainfall also happens in June, July, August. There are other details we'll come back to. You can see that because of the zonal scale here, the ITCZ remains clearly to the north over most of this region except in the west, whereas here you can see that it begins to knock on the equator during some seasons, and that makes for special variability of the ocean atmosphere system in here as well. And also the Indian Ocean has a special zonal variability or east-west variability, which in the Pacific is much more prominent, known as the El Nino or the El Nino Southern Oscillation. So again, just stare at these and make sure you can connect the various features and seasonalities to the various dynamics. There is the Amazon, for example, which gets rain pretty much throughout the year as well. Looking at the winds, sorry this figure is a little bit crowded, but I didn't know how to split it. It's basically showing mean sea level pressure and winds for June, July, August, SON, DJF, and MAM. And again, you can see the sea level pressure is low in the summer months because sun is overhead and there is a heating. Temperatures are warmer compared to, let's say, the winter months. So you can see winter, the pressure goes up quite a bit compared to the summer months, and then there is a transition during the autumn and spring months, and you see clearly these features of subtropical gyres over the oceans, which wax and wane with the seasons as the sun moves north and south, and the ITCZ moves north and south as well. And there is an out of phase relation between the hemispheres, obviously. So the tropics in general are low pressure regions. You can see the mean sea level pressure here is generally low compared to the seasonal ups and downs away from the deep tropics. So I don't know what else to point out. So here are the southeasterly trade winds, northeasterly trade winds coming into this ITCZ, which is the warm temperature and high rainfall regions. There is the SPCZ with pressure changing with season as well. Low pressure, bad weather, high rainfall, variable winds, high pressure, sinking motion in the atmosphere. This is where the Hadley cell comes down. So the ocean deserts and the land deserts are approximately at those same latitudes where the Hadley cell sinks. So sinking air, clear skies, high pressure, no rain, deserts, right? India is at the same latitude, but because of the monsoon circulation, it gets rain, and it's not so much a desert except in the northwest. So you can clearly see the differences here. The strong southwesterly wind, or the Findlater or Somali jet in the summer months, which puts rain over here because of the Western Ghats, and over the Bay of Bengal and the core monsoon zone. Low pressure associated with the monsoon is clearly seen here. And the winds transition to northeasterly into the winter months, where the ocean is warmer than land. Land cools rapidly again because of the sun going south and the low heat capacity. Pressure goes up, so you have a pressure driven flow that is going to be deflected by Coriolis. If you don't know Coriolis, I have a podcast on my channel as well. Basically, the easiest thing to remember if you don't know is that in the northern hemisphere there is a deflection to the right of the direction of motion because of Coriolis. In the southern hemisphere, there is a deflection to the left of the direction of motion. So, for example, here, land is warming faster in the summer because sun is overhead. So high temperatures, low pressure. Ocean warms slower because of the heat capacity. So higher pressure, colder temperatures. So if air wants to go from southern latitudes to northern latitudes, the Coriolis is going to tilt it to the right, so you're going to end up with southwesterlies. Okay, this is the simple way to think about it. And over the ocean, there is a convergence because Coriolis pushes to the right here, so you get flow into the middle. So we will see that later on. Whereas on the equator, flow is being pushed away from the equator on both sides, so the water is upwelled. So you get upwelling here, warming of these waters. They get moved by the winds from the upwelling regions towards these warm pool regions. Okay. I'm saying it in a hurry somewhat maybe, but not a big deal. These are simple things, and I have a course on oceanography where these things are explained in more detail, so you can go through those podcasts as well. Okay.